So let's say that we have this curve here, which we'll call f of x, and let's say that we need to find the area underneath the curve between x is equal to 0 and x is equal to 3, and we'll call this area r. So we need to find r. Well, as we know, we can find the exact area of r by integration. So we can integrate from the lower limit 0 to the upper limit 3 for fx dx. But as well as this, we can approximate the area of R using something called the Trapezium rule. So in order to do this, we firstly need to take points of equal x distances apart on f of x. So we'll do this starting from 0 and ending at 3. So let's say we do this at 0, 1, 2 and 3. Okay, so we have these 4 points here on f of x, which are at 0, 1, 2 and 3, and as I said before, these are all the same distance apart. They're all the distance of 1. And now what we're going to do for each of these points, we're firstly going to connect them to the x-axis like this here, and we're also going to connect the points to each other like this here. Okay, and then if you do this for all of the points, you end up with 3 trapeziums. You end up with this one here, which is between 0 and 1, and we're going to call this trapezium 1, or we're going to call it T1. And then we have this trapezium here between 1 and 2, and we're going to call this T2. And then we also have this trapezium here, which is between 2 and 3, and we're going to call this T3. It might be easy to see that these are trapeziums if we flip them over 90 degrees like this here. They have this shape, which hopefully you can recognize is a trapezium. And then the trapezium rule is that the area of R, which is the area underneath the curve, is approximately equal to the area of these 3 trapeziums added together. So R is approximately equal to the area of T1 plus the area of T2 plus the area of T3. And hopefully you can see why this is an approximation, because these 3 trapeziums combined does cover a lot of the area underneath this curve here. Now, it's not a great approximation. So for example, for T2 here, you can see that we have this section here that's not underneath the curve, but it is included in this trapezium here. So this trapezium, T2, is an overestimate. It's the same with this T3 here. We have this area that's not underneath the curve, but it is contained within this trapezium. And we also have this area up here that's actually an underestimate, this T1, because it doesn't include this area up here. However, if we reduce the distances between the points, so remember before we had the distances between the points as 1, if we half it to 0.5 like this here, firstly this is going to increase the amount of trapeziums. So remember before we only had 3 trapeziums, whereas now we have 6 trapeziums here instead. But if we make more trapeziums and we make the trapeziums thinner, it's going to become a better approximation. And hopefully you can see this. So for example, if we look at this section here, so before, when the distances between the points was 1, we had these 2 points here that were connected together in a trapezium, and we had this overestimation here. Whereas now, when we split it up into 2 trapeziums instead, you can see that this overestimation isn't as bad now, so therefore it's a lot better of an approximation. And then if you keep following this logic, if you keep making the trapeziums thinner and you keep using more trapeziums, you'll end up with a more and more accurate approximation. Okay, so we've shown that the approximate area of R is equal to the area of these trapeziums added together. So how do we actually find the area of these trapeziums? Well, if you don't know, the area of a trapezium is equal to h over 2 and then a plus b, where h is the height of the trapezium and a and b are the length of these 2 sides here. So if we consider this first trapezium here, remember this trapezium here is flipped 90 degrees, so that means that h is now going to be down here, and then this side here is going to be a, and this side here is going to be b. Well, let's consider h here at the bottom first. So this is the value that we've talked about before. It's the distance between these 2 points here, and on the previous slide we started with it being 1 and then we shortened it to 0.5. This is essentially the thickness of the trapezium. And what's important about this value is it's the same for all the trapeziums. It's the same value, which we're going to call h. For the sides of the trapezium, so the A and B here, you can see that for the trapeziums, it changes in length constantly, like this here, but this isn't the case for the thickness of the trapezium. They all have the same value, which we're going to call h. So now let's consider A and B. So remember, this is the x-axis here. So here, y is equal to 0. So for A, we need to find the distance between this point and this point here, and as this is y is equal to 0, therefore A is going to be equal to the y coordinate of this point here, and likewise B is going to be equal to the y coordinate of this point here. So therefore this point here, let's call this x0, y0, and for B, let's call this point here x1, y1. So therefore the length of this side here, A, is going to be y0, and the length of this side here, B, is going to be y1. So if we plug these values into this equation here, the area of this trapezium here is going to be h over 2 and then a plus b, so it's going to be y0 plus y1. So if we then consider the next trapezium, which is this one here, so now this side here is going to be a and this side here is going to be b. So we've already talked about this side here is going to be y1. And then this point here, if we call this x2, y2, therefore this side here is going to be y2. Remember, the thickness is the same, so therefore the area of this trapezium is going to be h over 2 and then y1 plus y2. And then we continue this pattern, so just quickly for the next trapezium, this is now going to be a, and this is now going to be b, so this is going to be y2, and then this point here we're going to call x3, y3, and then this side here is y3. So the area of this trapezium is going to be h over 2 and then y2 plus y3, like this here. And you can kind of see this pattern forming, this y0 plus y1, y1 plus y2, y2 plus y3. So if theoretically we had a fourth trapezium, it would be h over 2, y3 plus y4, like this here. So R here, where we have these three trapeziums, is approximately equal to the area of these three trapeziums added together. Okay, so to figure out an approximate area of R, rather than using 3 trapeziums, let's instead use n trapeziums. So what we're going to do is, rather than going up to x3, y3 and using 3 trapeziums, what we're going to do is we're going to go up to xn, yn, and we're going to use n trapeziums. Okay, so let's consider this. Remember, we need to add the areas of all n trapeziums in order to get the approximate area of R. So if we start with the first trapezium, it's just going to be the h over 2 y0 plus y1, then the second trapezium here, and then the third trapezium here. It's going to keep following this pattern like this up until the nth trapezium. So let's first consider the n minus 1th trapezium. Okay, so this is going to look like this here, where this point here is going to be xn minus 2, yn minus 2, and this point here is going to be xn minus 1, yn minus 1. So therefore this A side here is going to be yn minus 2, and then this B side here is going to be this yn minus 1, and then remember the thickness of the trapezium is always going to be this constant h value here. So therefore the area of this trapezium is going to be h over 2 yn minus 2 plus yn minus 1. Okay, so if we now consider the nth trapezium, this point here is going to be xn minus 1, yn minus 1, and this point here is going to be the xn, yn, so therefore this side here, A, is going to be yn minus 1, and this side here is going to be yn, again the thickness is h, so therefore the area of this trapezium here is going to be h over 2, y of n minus 1 plus yn. So therefore this is the formula for the approximate area of R, where it's all these trapeziums, so the first trapezium, the second trapezium, the third trapezium, and then however many trapeziums there are up to the n minus 1 trapezium and the n trapezium. Okay, so we're left with this formula here where r is approximately equal to the areas of all of these trapeziums added together, okay? And we can simplify this formula, firstly because h over 2 is common in all the terms, so therefore we can factorize this out and write it as r is approximately equal to h over 2, and then we're just going to be left with all of the y values in these brackets added together like this here. And then we can further simplify this because we have y values that repeat themselves. So for example, you can see that y1 comes up twice here. We've got two y2s here. If we wrote out the entire thing, we'd also have two y3s here as well. And this continues all the way up to yn minus 1, like this here. There are only two y values that don't repeat themselves, and that is y0 at the front here, which is on its own, and yn at the end here. So therefore we can simplify this formula and write it as h over 2, and then we've got this singular y0 here, and then plus 2, and then all of these y values here, and then plus the singular yn at the end. And then this is the formula for the trapezium rule here, and this is given to you in the formula booklet, so you'll have access to it in the exam. Now in the formula booklet they don't say that it's approximately equal to r, they say it's approximately equal to this integral here. And the reason is because remember we talked about at the start that we can find the exact area of r using integration. So we said that r is equal to the integral. Now in the example we used at the start, we said that the lower limit was 0 and the upper limit was 3. But to turn this into a general formula, let's say that the lower limit is c and the upper limit is d, and then we integrate y like this here. So therefore, as r is equal to this integral here, we can sub it out and write that this integral is equal to this formula here. Now this h value here, we've talked about what this actually means. It's the thickness of the trapeziums, but there's also a formula to figure out h here that's also given to you in the formula booklet, and that is that h is equal to d minus c over n, where d is this upper limit here and c is this lower limit, and n is the number of trapeziums that you're using. Now this formula is given to you in the formula booklet, but you'll find a lot of the time to find the value of h in questions you don't actually need this formula. There are easier ways that you can do it, as we'll see. Okay, so hopefully that all makes sense, but you might be wondering at this point what type of questions they can ask you. Well, they always have the same format. So here's an example where we have this diagram here and we're told it's of the curve with equation y is equal to x over 1 plus root x. Now for trapezium rule questions, the actual equation isn't usually that important. What's important is kind of the diagram here, and we're told about this region R, which is underneath the curve and lies between x is equal to 1 and x is equal to 3. And we're given this table here, which is values of x and y for this equation. So the x values are 1, 1.5, 2, 2.5 and 3, and these values of when you plug them into this equation, they give out these y values here. And we need to use trapezium rule to find an estimate for the area of R, okay? So it's all to do with this table here, okay? So what I've done, this diagram here, I've kind of enlarged it into this section here and want to show you what's going on. So this table here, these x values, 1, 1.5, 2, 2.53, and these y values that they give out, these are points on the curve, like this here. And as I said before, these are at the x values of 1, 1.5, 2, 2.5 and 3. And what's important about these values is they're all the same distance apart of this 0.5. And because of this, therefore, we can use the trapezium rule because they all have the same thinness. Okay, and then if you connect the lines, you get these four trapeziums here. So therefore we can use the trapezium rule. So we're going to use the formula for the trapezium rule, which is up here. So we need to find the values of h and then these y values here. Okay, well, let's start with h because this is easy. This is the thickness of the trapezium. And as we've already talked about, it's all the same value. It's all this 0 0.5. This is the distance between the x values here. So therefore, h is equal to 0 0.5 for all the trapeziums. So how do we figure out these y values? Well, we can do this by using this table. So if we consider these 5 points here, we can label them like we did before with this x0, y0, x1, y1, and then so on like this here. So if we consider this x0, y0, well, this is where x is equal to 1, so therefore we can just read off the table and see that y is equal to 0 0.5. So therefore y0 is equal to 0 0.5. And then by the same logic, if we go across one, this x1, y1, x1 is equal to 1.5, so therefore y1 is equal to the corresponding y value, which is 0.6742. And then it keeps going like this. y2 is equal to 0.8284, y3 is equal to 0.9686, and y4 is equal to 1.0981. And all we just need to do now is plug these values into this formula. Okay, so let's plug these values into the formula. Now, as the final y value is the y4, in this instance, n is equal to 4 with this equation here. So remember, we multiply all of the y values by 2. We put them inside this 2 bracket, except for the yn, so the y4 in this case, and the y0. So therefore, if we plug the values in, it's going to be half h, so it's going to be half and then 0 0.5, then it's going to be y0, which is 0 0.5, and then plus 2, and then put the y1, y2 and y3 inside the bracket with a 2 like this here, and then close the bracket, and then it's going to be plus y4, which is 1.0981. And then if you put this into your calculator, it wants it to 3 decimal places, it says in the answer, you get out a value of 1.635. So this is an estimate for the area of R here. Okay, so here's another past paper question to do with the trapezium rule. Okay, so for part A, we're given the table like before, where we have the corresponding x and y values for y is equal to log base 3 of 2x. As I said before, this actual equation here isn't actually that important, and you can see we have x values between 3 and 9, and we need to use the trapezium rule to find an estimate for the integral between 3 and 9 of this equation, log base 3 of 2x. Okay, so we need to use the formula for the trapezium rule here. So we need to find the value of h and the values of y here. Okay, well, let's start with h. So this is the thickness of the trapeziums, and you can see from 3 to 4.5, and then 4.5 to 6, 6 to 7.5, and 7.5 to 9, they have a constant difference of 1.5, which is the thickness of the trapeziums. So therefore h is equal to 1.5. And now we need to consider the y values. So we need to go from the lower limit 3 to the upper value, or the upper limit, sorry, 9. And therefore, as this x value here is 3, this y value here is going to be y0, which is 1.63. And then if we go across, y1 is equal to 2, y2 is equal to 2.26, y3 is equal to 2.46, and y4 is equal to 2.63. So therefore we can plug these values into the formula here. So it's going to be h over 2, so it's going to be 1.5 over 2, and then it's going to be these y values here. Remember, y0 and in this case y4, because this is the final y value, are not in this 2 bracket, but the other 3 values are like this. And then if you put this into your calculator, you get out a value of 531 over 40, or if you want to write it in a decimal, it's 13.275. Okay, and then for the first part of B, we need to use our answer to part A to estimate a value of the integral between 3 and 9 of log base 3 of 2x to the power of 10. Now, in part A, we did an estimate for this integral here of the same limits of log base of 3 of 2x. So the only difference here is we have this power of 10 here. And the way we're going to approach this is we need to consider the laws of logarithms. And you need to remember that when we have a power that's inside a log like this power of 10, what we can do is we can take it out of the log and make it a coefficient like this here. Go back to the video on laws of logarithms, you need a reminder of this. So therefore this is now going to become the integral between 3 and 9 of 10 log base 3 of 2x. And if you really want to, what you can also do is take this 10 out of the integral like this here. And what's key about this is if you compare this to what we did in part A, so this is what we did in part A. Now we've got the exact same log here, but now we've got a 10 in front of it. So therefore, as we've got an estimate for this integral here, what we can just do is multiply this estimate here, this 531 over 40, by this 10 to get an estimate for this value here. So therefore, if we do this 10 times 531 over 40, it's going to be 531 over 4, and if you want to write it as a decimal, it's 132.75. Okay, and then for the second part of B, we need to find an estimate for the integral between the same limits of 3 and 9 of log base 3 of 18x. And like before, we want to rewrite this so we have this term present, and therefore we can sub it out for the 531 over 40. And the key to this again is to use the laws of logarithms. So we have this 18x here, and what we can do is we can rewrite this 18x as 9 times 2x. And what's useful about this is if you remember the laws of logs, if you have two things that are inside a logarithm multiplied together, you can split up that log by adding two different logs together. So what we can do is we can rewrite this as log base 3 of 9 here plus log base 3 of this 2x. And you can see we have this log base 3 of 2x that we need to have to sub out this 531 over 40. And what's also nice about this method here is log base 3 of 9, if you figure it out or just put it into your calculator, simplifies down to 2. So therefore we have quite this nice thing here of this integral of 2 plus log base 3 of 2x. So what we can do, as we have two terms in this integral, we can split this up into two different integrals. So if we first focus on this integral between 3 and 9 of 2, so the integral of 2 is equal to 2x, so therefore if you sub in the limits, the upper limit here of 9 and the lower limit here of 3, we get this expression, and if you figure this out, it's equal to 12. So therefore this integral here is equal to 12, and then we have the integral between 3 and 9 of log base 3 of 2x, which is this term here. So the estimate of this is 531 over 40, and then 12 plus 531 over 40 is equal to 1011 over 40, or if you want to write it as a decimal, it's 25.275. Okay, so here's another past paper question on the trapezium rule. Okay, so for this question, we're shown this graph here, and this graph shows a sketch of this curve here. As I've said before with trapezium rule questions, this equation isn't actually that important. And we're told about the region S, which is this region here. And region S is underneath the curve, and it lies between x is equal to 1 and x is equal to 3, and we're given this table like before with corresponding values of x and y for this equation here, between 1 and 3 for x, and for part A we need to use the trapezium rule to get an estimate for this area of S here. So as it's underneath the curve between 1 and 3, we can use the trapezium rule, and we can use this table here as it lies between 1 and 3. So if we use this formula up here, we need to find h and we need to find the y value. So if we start with h, if you look at the x values, you can see that as we go up like this, they all have the same difference. They're all 0.5. 0.5, so therefore h is equal to 0.5, and therefore if we're starting with x is equal to 1 here, therefore y0 is going to be equal to 3, y1 is going to be equal to this 2.3041, then it's going to keep going up like this until y4 is equal to 2.2958. So therefore we've got all the values for the trapezium rule formula, so therefore we're just going to sub the values in. So it's going to be 0.5 over 2, then it's going to be y0, which is 3, and then plus 2, and then y1, y2, and y3, and then finally y4 here. And then if you put this here into your calculator, you get out a value. It wants it to 3 decimal places. You get out a value of 4.393. Okay, and then for part B, we need to explain how the trapezium rule can be used to obtain a more accurate estimate for the area of S, and this is just a 1 mark question. Now I'm just going to put up the mark scheme for this question. Now this is kind of what I talked about at the beginning of the video of how the trapezium rule works. The way you get the trapezium rule to be more accurate is by using more trapeziums and to use thinner trapeziums, so decreasing the value of h. So if you just say anything like that, increasing the number of trapeziums, that will get you the mark. Okay, and then for part C, we need to find the exact area of S, and we need to show it can be written in this format here. So S lies underneath this curve here with this equation, and it lies between x is equal to 1 and x is equal to 3. So therefore we can use integration, and we can find the exact area of S by integrating between the lower limit of 1 and the upper limit of 3, this equation here. So x squared natural log of x over 3 minus 2x and then plus 5. Okay, so now all we need to do is actually integrate this here and show it can be written in this format. Now, as I've talked about before with definite integrals in this chapter, these limits here of 1 and 3, we don't actually need to worry about these at the start. We plug these in at the end. What we first need to do is actually focus on integrating this function here. So let's first focus on integrating this here. And just by the way, I've rewritten this x squared natural log of x over 3. I've rewritten it as 1 over 3 x squared natural log of x, as this is just a bit easier to integrate. Okay, so we have 3 terms here, and as I've talked about before, when we have multiple terms, we can consider the terms individually and integrate them individually to stop us from kind of getting overwhelmed. So let's do that. So let's start first with this 1 over 3 x squared natural log of x, and I've taken this 1 over 3 out of the integral like this here, so we can focus on integrating this x squared natural log of x. Now here we have 2 functions that are multiplied together, so the way that we integrate this is using integration by parts. Now I've done a video already in this chapter on integration by parts, so go back to that if you need a reminder of how it works. I've given you the formula here for integrating by parts, because remember this is given to you in the formula booklet, so you'll have access to it in the exam. But the way that we do integrating by parts is these 2 functions here, we're going to call one of them u, and we're going to differentiate that function, and we're going to call the other function dv over dx, and we're going to integrate that function. So what function are we going to call which? Well, as we talked about in that video, the natural log of x, we don't want to call this dv over dx, because that means we're going to have to integrate it, and it's quite difficult integrating the natural log of x. What we would prefer to do is call u the natural log of x, so we differentiate it instead, which we can do, and therefore we'll call the other function, this x squared, we'll call this dv over dx. Okay, so let's start with this u is equal to the natural log of x, so if we differentiate this, it's going to be du over dx is equal to, and we talked about this in the differentiation chapter of year 2, when we differentiate the natural log of x, it's equal to 1 over x, and then if dv over dx is equal to x squared, if we integrate this, it's going to be v is equal to, and then when you integrate x squared, this is just year 1 integration, is equal to 1 over 3 x cubed. So therefore we need to plug these values into the integration by parts formula. So it's uv, so u is equal to the natural log of x, and v is equal to 1 over 3 x cubed. So therefore uv is going to be 1 over 3 x cubed, and then the natural log of x. Remember, we need to put back in this 1 over 3 that we took out at the start and multiply everything by this, and then it's going to be minus the integral of v du over dx. So v is equal to 1 over 3 x cubed, and du over dx is equal to 1 over x. So if you do x cubed multiplied by 1 over x like this here, it will cancel down to x squared. So therefore this will be equal to 1 over 3 x squared, and I've taken the 1 over 3 out of the integral like this here. So we're left with this here, and we can simplify this because the integral of x squared is equal to 1 over 3 x cubed, and then we can further simplify this by multiplying this 1 over 3 here by this 1 over 3, so it becomes 1 over 9 x cubed, and then the natural log of x, and then we can multiply this 1 over 3 by this 1 over 3, and then this 1 over 3 as well, so it becomes 1 over 27, and then remember we have a minus here in front of this integral, so it's going to be minus 1 over 27 x cubed. So that's how you integrate this here. And then if we focus on the other two functions, which are a bit easier, so if we focus on this minus 2x, again I've taken the minus 2 out of the integral like this here. If you integrate x is equal to half x squared, and then minus 2 multiplied by half is equal to minus x squared, and then if you integrate 5, it's just equal to 5x. So therefore, if we integrate this entire function here, it's going to be these terms added together. So it's going to be 1 over 9 x cubed natural log of x minus 1 over 27 x cubed minus x squared plus 5x. Okay, so we have this function here, so now we just need to plug in the limits of 3 and 1. So if we start with the upper limit 3, so we plug 3 in for all of the values of x, and then we do minus, and then we plug in the lower limit of 1 like this here, and then we can do some simplifying. So we have this 3 cubed here, which is going to be 27, and then it's going to be divided by 9, so this is going to be 3, then it's going to be the natural log of 3. 3 cubed is 27, and that's going to be divided by 27, so this is just going to be 1. 3 squared is 9, 5 times 3 is 15, and then remember it's minus, and then we have the natural log of 1 here, so this term here is going to cancel out. We have 1 cubed here, which is just 1, so this is going to be minus 1 over 27, but remember we have this minus here, so it will cancel out, and then 1 squared is just 1, and then again this minus here will cancel out, and then 5 times 1 is 5, and then it will be minus like this here. And then all of these kind of numbers here, if you put this into your calculator, it gives out a value of 28 over 27. Okay, so we need to write it in this format here. So the a over b is this 28 over 27 part, so we've got that part correct, and we need the natural log of c, and the problem is at the moment is we don't have a coefficient in front of this natural log here, but we do here. We have this 3 here, so we can't actually have this, so this isn't the final answer. So what we need to do is we need to bring this 3 into the natural log here, so it becomes the natural log of 3 cubed plus 28 over 27, and then 3 cubed is 27, so it's going to be the natural log of 27 plus 28 over 27, and this here is the final answer in this form. Okay, so here's one last past paper example question on the trapezium rule for you to have a go at. So pause the video, have a go at the question, and I'll go for the answer in about 5 seconds. Okay, so for this question, we're told about a curve that has equation y is equal to fx. We're not actually told what the function is, but kind of like what I've talked about before, the function isn't actually that important. And we're given this table here, like before, for x and y, between x is equal to 3 and x is equal to 4. And a is the y value when x is equal to 3, and b is the y value when x is equal to 3.4. And we're told that this table is used for the trapezium rule to find an approximate area between x is equal to 3 and x is equal to 4. And we're told that this calculated area is 17.59, and therefore we need to show that this here is true. Okay, so what we need to do is we need to use the formula here for the trapezium rule and sub in the values, and we know that this formula is equal to 17.59, and then rearrange it to this form here. Okay, so let's get the values of h and y. So let's start with h here, and as you can see, 3 to 3.2, 3.2 to 3.4, and so on. They all have a difference of 0.2. It's all constant for this for all of them, so therefore h is equal to 0.2. That's the thickness of the trapeziums, and therefore we can figure out the y value starting from x is equal to 3, because this is where it starts and it ends at x is equal to 4. So y0 is equal to a, y1 is equal to 16.8, y2 is equal to b, y3 is equal to 20.2, y4 is equal to 18.7, and y5 is equal to 13.5. So we can sub these values into this formula. So we get the h over 2, which is 0.2 over 2, and then it's going to be y0, which is a, plus 2, and then y1, y2, y3, and y4, and then y5 on its own at the end here, and all of this is equal to 17.59. Okay, and we need to rearrange this in order to get it in this format here. Okay, so firstly, 0.2 divided by 2 is 0.1, and we're also going to expand this bracket here so it gets in this form here. And then what we're going to do is use a calculator to add all of these numbers together like this, and if you do this, this is equal to 124.9. okay, so we're left with this equation here. Okay, so what we can do is we can divide both sides by 0.1 to get rid of it on this side, so we get that a plus 2b plus 124.9 is equal to, and if you divide this by 0.1, it's equal to 175.9. It's the same as multiplying it by 10, and then move this onto the other side, so we get that a plus 2b is equal to 51, which is what's required. Okay, and then for part B, we're told that the sum of all the y values in the table is 97.2, and therefore we need to find the values of A and B. So using this information, we can create an equation, because the sum of all the y values, so all of these values added together like this here, is equal to 97.2, and then we can simplify this because we've got all of these numbers here added together. So if you put this into your calculator, these are equal to 69.2, and then if you move this 69.2 onto the other side of the equation, you get that a plus b is equal to 28. And what's useful about this is we now have a pair of simultaneous equations. We have this a plus b is equal to 28, and we also have this a plus 2b is equal to 51 that we figured out in part A. So now what we can just do is find the values of A and B. So it's really easy using this pair of simultaneous equations to find b, because we just find the difference between the two simultaneous equations, and we get that b is equal to 23, and therefore we can sub this b is equal to 23 back into this a plus b is equal to 28 here. So we get that a plus 23 is equal to 28, so move this onto the other side, so we get that a is equal to 5. So a is equal to 5 and b is equal to 23.